Hello and welcome to this short video, an introduction to Lasso with an example in R. My name is Alex Code. You can find details on the data and R code in the description in the text box below the video if you want to follow along with this example in R. Okay, so let's start by thinking about signal and noise. Statistical data are measurements that are hopefully accurate, but they may contain noise. High quality data has a high ratio of signal to noise. Signal corresponds to the valuable part of statistical information. Signal is the persistent pattern that is stable across different samples of the same process. Noise, in a regression context, corresponds to the unexplained residuals or error terms in regressions such as OLS linear regression. Noise can also refer to spurious correlations across variables, which are non-zero correlations that have no clear interpretation. Noise can correspond to the spurious variables in a regression model that might be statistically significant in one particular data sample, but are not likely to be statistically significant in other data samples. Noise leads to situations of false positives and false negatives. A false positive would be a variable that looks statistically significant in some regression output, but it should not really be considered to be a useful predictor. A false negative would be a variable that is not statistically significant in some regression output, but in fact it should be included in the set of important predictor variables. The graph on the left shows the case of applying a linear regression to data that is clearly non-linear. The data seems to display a U-shape. The graph on the left is the case of underfit. A more complex model, i.e. a non-linear model, would do a much better job of fitting the data. In the center, we have a non-linear regression line that fits the data fairly well. It picks up on the main trends, although it does not perfectly predict the positions of all of the data points. On the right, we have the case of overfit. The theoretical model fits all the data points exactly. It is too good to be true. Such a theoretical model might perform well on the data it is trained on, but it is unlikely to perform well when applied to new data. The problem of overfit refers to the idea that a model that works well in your historical training data might not work well in new data that you collect, referred to as test data. There is a crucial distinction between in-sample predictive power, which comes from fitting a model to training data, and the out-of-sample predictive power that comes from applying the model to new data. With modern data science, there are powerful tools for fitting models to data, and overfitting is a real problem. Given that these data fitting techniques are so powerful, we do not care at all about the R-squared statistic or model fit that comes from fitting the model to the historical training data. The only thing that matters is the out-of-sample R-squared statistic that comes from applying the model to new test data. We don't care at all about the in-sample R-squared from the historical training data because we can always increase the in-sample R-squared just by adding spurious variables and overfitting. Overfitting is particularly problematic with high-dimensional data, for example if you have hundreds of explanatory variables or features in your regression model. In the classic case of OLS linear regression, the number of explanatory variables is much smaller than the number of observations. This is the case of the figure on the left for OLS regression in a low-dimensional setting. If the number of variables p is greater than or equal to the number of observations n, then OLS perfectly predicts the data. This is the case of the figure on the right. The resulting linear model would have perfect predictive power on the historical training data, but will perform badly when applied to new data. It may even have a negative R-squared statistic on new data, indicating that it performs worse than having no model at all. Lasso is a big data technique that is designed precisely to deal with the risk of overfitting that comes from powerful data fitting techniques and high-dimensional data. Let's compare Lasso to the well-known OLS linear regression model. With OLS, the idea is to fit a regression line that minimizes the residual sum of squares, RSS. With Lasso, the difference is that you add on a penalty term, shown here in red, that puts a price on model complexity. The penalty term wants to shrink the regression coefficients to be as close to zero as possible. If you force the estimated coefficients beta hat to be closer to zero, then the predicted y values y hat will be closer to y bar, the average value of y. With Lasso, the estimated regression coefficients beta hat have to justify why they should take non-zero values. This slide compares OLS and Lasso in the case of 6 explanatory variables. 6 variables is a very small number of variables for discussions of Lasso. Overfitting is not so important when you only have 6 explanatory variables, but it is more important when you have 600. But anyway, let's stick with this example of having just 6 explanatory variables. With OLS, you have many coefficients that are nearly zero, but it is very unlikely that the coefficients are exactly zero. That means you have non-zero coefficients and a long list of explanatory variables. With Lasso, the penalty term shrinks unimportant coefficients to zero and then simplifies the model. Here we have coefficients on x2, x3 and x5 that are shrunk to exactly zero. This means that we can remove these 3 terms from our Lasso regression equation, which simplifies our model. Lasso is useful because it is a meaningful way of getting rid of relatively unimportant predictor variables. An alternative approach could be manually checking each of the explanatory variables and deciding whether to keep it in or throw it out of the regression model, but this hand-picking of variables would take a lot of time. This figure shows how Lasso shrinks the coefficients towards zero. Irrelevant variables lead to unnecessary complexity in the regression model and lead to the problem of overfitting, so we would prefer to drop them. We can remove irrelevant variables by setting their coefficients to exactly zero. OLS linear regression would give these irrelevant variables a small non-zero coefficient, but OLS is extremely unlikely to give coefficient estimates that are exactly zero. Lasso shrinks some coefficients to be exactly zero, which is why we can also think of Lasso as a technique for variable selection, because an explanatory variable with coefficient 0 is effectively dropped from the regression model. Note, however, that Lasso does not try to shrink the value of the regression intercept term. The overall Lasso procedure boils down to 2 steps. First, get the 100 model estimates corresponding to 100 different values of the penalty term lambda. Then, in the second stage, select the best model from these 100 candidate models using a criteria such as the AICC, the corrected Akaike information criterion. For me, the hard part is getting the data in the right format for gamlr, which is the R command that we will use for Lasso. This slide shows a Lasso path plot, which, as we will see, is part of the Lasso output in R. On the horizontal axis, at the bottom of the graph, we see log lambda, which represents the values of the penalty term lambda. On the vertical axis, we have the sign and magnitude of the standardized coefficient. Along the top of the graph, we have the number of non-zero coefficients, starting out at 98 on the left and ending at 1 on the right. At the extreme right, the value of the penalty term lambda is very large, and this means that most coefficients are shrunk down to 0. At the very extreme, there is only one variable that remains in the model. At the extreme left, the value of the penalty term is so low that it has a negligible effect. At the extreme left, we have about 98 variables in the regression model, and the regression model is similar to a standard OLS regression that includes all of the explanatory variables. Each vertical slice of this graph corresponds to a regression model. This graph actually plots the output of 100 regression models. The best regression model, as selected by the AICC, is the model represented by the dashed vertical line in the middle. Care is needed to prepare the data for Lasso estimation with the gamlr command. For continuous variables, referred to as numeric variables, you need a column for each variable. For categorical variables or factor variables, you need a column for each level of the variable. If the variable is binary, it has 2 levels and so will require 2 columns. Gamlr requires a full set of levels for the variables. Do not drop the baseline reference case. When penalizing coefficients, the factor reference levels now matter. Instead of choosing the factor reference levels at the start, we let the right choice of factor reference level be decided by the Lasso algorithm. You are shrinking towards a shared mean with only significantly distinct effects getting non-zero coefficients. We also need to delete the intercept term, which is a column of 1s, as we prepare the data for gamlr. We also need to convert the data into a sparse matrix format, which helps to reduce storage needs and increase efficiency, thus requiring less memory and allowing for faster optimizations. For Lasso to work well, the variables should be on comparable scales. In other words, your model fit should not change if a measurement is in millimeters, centimeters, or meters. Fortunately, gamlr automatically standardizes the variables. Each regression coefficient beta's penalty is measured in terms of 1 standard deviation change in the explanatory variable x. Our data come from the EU Industrial R&D Investment Scoreboard, and you can see the link here on this slide as well as in the text below the video. This is data on the world's largest R&D investing companies. We start with 21 variables and 2,500 firms in the data. The top ranking R&D investors in this dataset are Alphabet, Meta, Microsoft, Apple, and Huawei. Then we do some data cleaning and preparation to get the data ready for Lasso. First, we tidy up the column names to make it easier to understand the data columns. Second, we convert some variables to become factor variables, that is, categorical variables. Third, we take logarithms, or the IHS, the inverse hyperbolic sine transformation, for some variables. Fourth, we remove unnecessary variables. And fifth, we decide what to do with cases of missing values. Now we have to build the model matrix for gamlr, where gamlr is the command that we will use for Lasso. In our case, the dependent variable that we are trying to explain is R&D intensity. We create a separate vector called YSB for the response variable y. Then we create a matrix of features or explanatory variables in sparse matrix format and remove the response variable y, shown here in terms of minus y col, and also remove the intercept term by adding on -1 at the end. Then we do the Lasso estimation using the command gamlr and also getting a Lasso path plot. The simplest regression model on the right, with the highest value for the penalty term, log lambda equals around 8, has only one explanatory variable. Over on the left, we have the regression model with the lowest value for the penalty term, where we have about 98 explanatory variables in the model if the value for log lambda is about -6. The dashed vertical line is the preferred model according to the AICC statistic, the corrected AIC. We can then examine the gamlr output. There are 100 different regression models in the matrix beta, which correspond to the 100 different penalty weights or segments of lambda. The coefficient matrix beta has dimensions 101 times 100. There are 101 variables and 100 different regression models. Because of the penalty term lambda, most of the models have far fewer than 101 variables, because most of the explanatory variables will be shrunk towards 0 and then excluded from the regression model. The best fitting model is the model at segment number 54. We can see that in this model, lots of coefficients have been shrunk down to 0 and then dropped from the regression model. If we drop the intercept term, we can see that there are 20 non-zero coefficients. The 5 most negative coefficients are country dummies for Indonesia and for Switzerland, the logarithm of employment, a country dummy for Japan, and a dummy for the automobiles and parts sector. The 5 most positive coefficients are a country dummy for China, some sector dummies for the sector's technology, hardware and equipment, pharmaceuticals and biotechnology, and software and computer services, and also the logarithm of sales. Another thing we can do is to check the coefficients for specific variables. Here the coefficient for profitability is minus 0.747, while the coefficient for sales growth is minus 0.00599. Both of these variables seem to be negatively associated with the dependent variable, which is R&D intensity. The coefficients for the 2 other variables here, logarithm of market capitalization and employment growth, are shrunk to 0 and therefore dropped from the regression model. And finally, another thing we can do is to use our Lasso selected regression model to focus on the predicted values of the outcome, which is R&D intensity, for specific firms. Let's focus on the 2 largest R&D investors, Alphabet and Meta. We can see that the actual R&D intensities are 14.0% for Alphabet and 28.8% for Meta. Then we can compare these to the predicted R&D intensities, which are 3.53% for Alphabet and 18.59% for Meta. The difference between the actual R&D intensities and the predicted R&D intensities suggests that Alphabet and Meta have higher R&D intensities than we might think, based on their characteristics. The difference between the actual R&D intensities and the predicted R&D intensities could also suggest that our model for predicting a firm's R&D intensity is not always so accurate. Suggestions for further reading are shown in the text box below the video. And that's all from me. Thank you for listening and have a nice day.